Hello everyone. Today we're going to solve problem 75 in DeepML, which is generate a confusion matrix for binary classification. Now, this is a very special problem for me because it's the first one that I made that got accepted into the website. And so you're going to get the official solution from the person who made the problem themselves. Now, this is a question that's part of a series of questions. I'm going to make a video on the one that comes after this one, but this one is thought for beginners. And so most of what I'm going to explain here in the video is going to be geared towards absolute beginners who are just getting exposed to the concept of confusion matrix and have no idea how to code it up. If you're a more advanced person, you may have been able to figure out how to code this on your own. You may also know that there's a API from, I think it's sklearn, in which you can generate the confusion matrix with one line. But I think it's important for beginners to understand how to do these kind of things from almost scratch to get an idea of what they represent and what they mean. So without any further ado, let's dive into the problem. So in the problem, we're tasked with generating a confusion matrix from the results of a binary classification model. And when we say binary classification, what we mean is that the output is either 1 or 0. I'm going to give a little bit of a motivating example afterwards, but for now, think that the format of the data is such that what you get here is the actual value of the observation that you're looking at. And then the second element is going to be the predictive value of your model. Now, you don't have to generate a model here. You're just working with the fictional outputs from this model. So given this information, you have to generate a confusion matrix, which is going to be a 2x2 matrix that has a certain format that we're going to talk about in a moment. Now, you may be thinking, what is this confusion matrix? What is this output of the model? What it is that you're talking about? So let me give you a little example. Let's say we have a model in which we're trying to figure out whether a phenomenon happens or not. So let's abstractly, let's say we have a data set with pictures, and we have, for example, pictures of cats. This is a terrible cat, but it is a cat nonetheless. And you can also have pictures in your data sets of stuff that are not cats. So for example, you would have a person, right? And so your model, what it's going to do is going to answer the question, is this photo a photo of a cat? So in this case, what we have here, which is a photo of a cat, should output 1. Yes, it is a photo of a cat. In this case, this is a photo of a person, it should output 0. Now, that's the idea. That's what we know, or rather what we're going to call the true labels. But let's think about more of edge cases. So for example, let's say it's kind of hard to do with just black and white, but for the sake of argument, let's say we have a picture of a man and a cat, right? So now, depending on how you phrase your model, you're going to expect something different from this. What I mean by that is that, let's say that our model tries to figure out if there's a cat in the photo. And in this case, yes, there is a cat in the photo, right? So the true label should be 1. But now it could be, it may not be, but it depends on how you train your model, that the model looks at this photo and says, you know what? This is not a cat. This is a 0. So this is the prediction of the model, which I'm going to abbreviate as pred. So in this case, what we have is that our model is predicting 0, which is that there's no cat, when in reality, a cat is there. The label should be 1. So there's a discrepancy between what your model is outputting and the actual value of the observation that you're looking at. When you're trying to summarize all of this information in something that's easy to see, is when you refer to what we're going to call a confusion matrix. Oh my God. A confusion matrix. And so a confusion matrix has a particular shape. It's a 2x2 matrix in which we have true positives, false negatives, true negatives, and false positives. Now, you may have heard these terms before, and there's a mathematical formula for this, which I go into more depth in the next video, in which I talk about the follow-up to this question. But just to give you the intuition and not the mathematical expression for these kind of things, which we're going to talk about later, a true positive is something that in the figure, it is a 1, that is a cat picture that has a picture, a cat in the picture, and that is labeled as such. So this would be a true positive in this case. A true negative, similarly, would be a case in which we have a picture of something that's not a cat, for example, here, just a human, and it's predicting a 0. It's predicting no cat. When in reality, there's no cat. This is what we're going to call true negative. But then we have the cases like this one, in which we have a picture that has a cat and is mislabeled. It's classified as a 0. This is what we would call a false negative. Why is that? Well, because the model is saying that there's no cat. It's labeling as negative, when in reality it should be a 1. It should be positive. It should be a 1. It should be from the positive label. And so we have a discrepancy here. So in order to visualize how many of these discrepancies we have and of which type they are, that is, whether we're misclassifying a cat picture as a non-cat picture or a non-cat picture as a cat picture, we construct this confusion matrix. So that's the gist of it. That's the idea. And that's the phenomenon that we're capturing when we're making this matrix. Okay, so now we know what a confusion matrix is. So how do we get these numbers right here? And remember what I said about the input. So the way the input is formatted, we're going to have a list of lists, that is multiple lists in which we're going to have only 2 elements. And each of them are going to have, in the first position, the actual value of that observation. And on the other value, the prediction of the model. So for example, here is 1, 1. It means that for the observation at index 0, the true label was 1. That is, it was a cat picture, and it was labeled as a cat picture as well. This is prediction. Now you can have all of the combinations that we have here. For example, 1, 0, which means that it was a cat picture, but it was labeled as a non-cat picture. And so that's going to be a false negative. Then we have the case of the false positive. Then we have the case of the true negative, and so on and so forth. So this list is going to be of the size of all of the observations that you have. So this problem, what we all talked about, just summarizes to counting how many of these different lists show up, right? Because if you manage to get the count of all of the lists that are of the shape 1, 1, you're going to get the number of true positives in your model. Similarly, if you were to count all of the 0, 0s, you would get all of the true negatives in your model, and so on and so forth. So although we're dealing with a somewhat high-level concept here, which is the confusion matrix, this problem is relatively straightforward in that once you figure out what it is that you have to do and what it is that a confusion matrix represents, the only thing that you have to do is count. Now, there are many ways in which we can count on this code using Python. What I'm going to show you in the official solution is a somewhat straightforward way of counting, which is using this function named counter, which comes from the one of the standard libraries in Python. And what counter does, it looks at a list, in case you've never heard of this, it looks at a list and tells you for every value in the list, what is their frequency. That is the count, how many times that value in the list shows up, which is perfectly suited for what it is that we have to do. So now that we understand what the high-level idea is that we have to do, I'm going to teach you how to do it on code. Great, so now let's dive into the code. As I said before, we're going to utilize this very nice function counter to count how many occurrences of each element in the list occurs. So the way you do this is you're going to, let me make a comment, count instances of all of the elements. The way you utilize counter is you just call counter and then pass a tuple of the information that you're dealing with. Now you may be wondering, why am I doing this? Well, you have to count something that can be hashable. I don't want to get into the specifics of it, but just know that if you're doing a dictionary, for example, in Python, you cannot use a list as the keys. You have to use a tuple if you want to represent information in this kind of way. And so we have to convert all of these lists that are inside of our big list into a tuple. Why? Because we want the position of 1, 1, 1, 0, 0, 1, 0, 0, because we talked about how each of them represented different things. Okay, so what this is going to do is this is going to generate a dictionary in which the key is going to be true and predicted, And then the value is going to be the count of that instance, which is exactly what we're doing. So once we get that, we're going to retrieve the metrics out of this thing. And the way we're going to do that is we're going to call to this instance of the element counts, and we're going to pass as a tuple the elements that we want. So remember, if we have 1, 1, that is the true label is 1 and the predicted is 1, then we have a true positive because it's a positive element that's been labeled as the positive class, which is 1. Now, a false negative is something that is positive in reality, but is labeled as negative. Similarly, a false positive is something that is false in reality, negative, but is labeled as positive. And finally, the true negative is something that is negative in reality and labeled as negative by our model. So now that we have that, we have to define the matrix. And so notice how I put them in order. As I said before, confusion matrix is simply a 2x2 matrix in which the elements follow a specific order, and that order is the same order that we have here. So it's going to be true positive, false negative, and we're going to pass false positive and true negative. And then finally, we're going to return this confusion matrix. And so I submit the code. I've forgotten to log in. And there you go. All of the test cases are accepted. So as you can see, this is a very straightforward problem, and it's great for beginners because you have to figure out what it is that you have to do and how you can generate all of the true positive, true negatives, false positive, false negatives based on the way the data is formatted. As I said, in the next video, we're going to talk about the follow-up to this question, in which we're going to generate a lot of performance metrics, and we're going to talk about what it is that they represent, why are they useful, and it's going to be a great video for beginners. So stay tuned, and I hope to see you on the next one.